Okay, so have you guys tried this one? How do you like it? Is it okay? Or you have a good sleep? Okay, either case, okay. So let's continue, okay. So we talked about like several, substitution method already. And I told you recursion tree is good for intuition, but it's not a formal proof. And the last one is the master method. It's more like a, what should I say, like a 代公式. Okay, just like give you like this format. If your recurrence relation is this shape, then you can directly apply like a master method to get the tight bound. Okay, so if your recurrence relation like this, T of n equal to A times T of n divided by B plus F of n, okay, where A greater or equal to 0, B is greater than 1, and F is asymptotically positive. Okay, if your recurrence relation has this format, which happen to be very common, because like the reason for that is because, like, remember I keep telling you guys, recurrence relation, the biggest source of the recurrence relation come from like divide and conquer, right? So in divide and conquer, you usually break the problem into a number of smaller problems, and usually it's broken into equally sized smaller problems. So you have like n divided by b. Okay, so you have like this size of subproblems, and if you have to solve every such subproblem, then of course you'll be b times t of n divided by b. But I mean, sometimes you don't need to solve everyone. Sometimes you don't need to solve everyone. So it could be like this part could be smaller than b. Sometimes you need to, in some particular example, you need to solve like even though the original problem size is n, you need to solve like more number of smaller problems. So this A could be greater than B in some occasions. Okay, so this A and the B, a lot of time they are the same, but sometimes A could be bigger, sometimes A could be smaller. Okay, depending on the problem, of course. Okay, and then this is divide, right? Divide the cost. To solve like every subproblems, and then the total cost. So A times this, and you also need the cost to merge them. Okay, to merge them. And to give the answer for the original the problem. So this is like a f of n. This is the cost. For the merge. So as I already told you. So this is like a very, very common situation in divide and conquer algorithm. Okay. So even though master method, I say like this is like what should I say, like 代公式嘛, just like just follow these rules and you get your answer. And but we know like a recurrence relation could be many different format. For example, like this. You can see, as I already told you, this doesn't look like a something that comes from the divide and conquer. But obviously, this is a recurrence relation, right? So there are so many different choices of recurrence relations out there. But as long as it comes from the divide and conquer, it should always look like this. And so this is fortunate because we have like a method that can help you to directly solve them. Okay. So what will be the what's the rule? Okay. So there are three type of situations. Okay. The first one, basically, you always need to check n to the power of log base ba. Okay, so log a with b as basis. Okay, you know log, right? So for example, log base 2, 4 is 2, right? Okay, things like that. Okay, so you need to check like the order, this order. So if your fn, if your f of n, this one, the merge cost, the cost of the merge, okay, is like bounded by this order, okay, minus a very, very small constant, where epsilon, it could be any constant, as long as it's greater than 0. Okay, so if that's the case, then we say fn grows polynomially slower than this one, so the solution will be, T of n solution will be theta n log ba, just this one. Okay? So, on the other hand, if they are, they are the same. This is n log ba times log k, log n to the power of k. Okay, if this is the case, if this one and this one, they are of the same order. If that's the case, then, we say, okay, this and this merge cost and this one grow at the same rate. So the solution will be this thing, okay, the original this, times another log n. So it'll be log n to the power of log ba times log n to the power of k plus 1. So that's the second case. The third case is, f of n, is like big omega n to the power of log ba plus epsilon. Okay, the first one is big O. The third one is the first one is like a upper bound. The third one is a lower bound. Okay, so if that's the case, we say f of n, the merge cost, grows polynomially faster than n log ba, and then and f of n satisfy the regularity condition. Okay, what is regularity condition? Okay, so a times f n divided by b is smaller or equal to c times f of n for some constant c. To be honest, this thing is usually the case. Okay, then the solution T of n is theta f of n. So we have these three cases. Okay, a little bit complicated, but it's rather. You can apply it a few times and get a hang of it. Okay， 就是说它比较复杂一点，但是如果说你练习几次，你应该蛮容易可以上手哦。We will try to use a recursion tree to explain like this method theorem later, okay? But let's first look at some examples, okay? Let's first look at some examples. First one, t of n equal to 4 times t of n divided by 2 plus n. So you can see that, okay? So this is, you break the problem into half, but you need to solve 4 such subcases, okay? And then the merge cost is linear. So we know like A is 4, B is 2. So when you consider n to the power of log base BA, it's like, base is 2, A is, 4. So log base 2, 4, so it's a 2. So n squared, okay? We know like, this n squared is like, some positive constant, order higher than your merge like a cost, which is linear, okay? So it will be case 1. Okay, if this is a case 1, then your t of n is this one, n to the power of log BA, so which is a theta n squared. So it's a, you just check. Okay, this one. And then the other one, t of n is 4tn divided by 2 plus n squared. Okay, this term it remains the same, but this one becomes n squared. Okay, and if you remember, like n to the power of log BA is still n squared, right? So this n squared and the merge cost n squared, they are the same. If they are the same, that falls to case 2. Okay, in the case of case 2, it's basically like n squared times log n. Tn will be n squared log n. Okay, you just apply master method and you get an answer very efficiently. Okay. The third one, the first is still 4tn divided by 2, okay, plus n cubed. Okay, so you have like this part is changed to cube. So obviously A is 4, B is 2, and the log n to the power of log BA is still n squared. But f of n, the merge cost is n cubed. So in that case, the merge cost dominant, everything. So the f of n is just like theta n cubed. Actually, you do need to check like this regularity condition. 4 divided by n divided by 2 to the power of 3. Is it small or equal to c n cubed or not? I mean, this can be easily checked. I mean, as long as you can make c equal to 0.5. I mean, this regularity condition is satisfied. But as I said, most of the time this is like a given. So you have like a theta n cubed as a tight bound. Okay, so of course this like what should I say, like these examples looks like straightforward. Okay, straightforward. Okay, but the question is how do we get it? How do we get this like couple of like thing? Oh, let's finish this one, the last one. Tn equal to 4tn divided by 2 plus n squared divided by log n. So this is like we still have like a A is 4, B is 2, so n to the power of log BA is still n squared. And f of n is this one. Okay, so in this case, okay, because like what should I say? Like let me put this. The third case, the second case, okay, it's not the fourth case. Third case, it's not the first case because like let me go back. This one and this one, they are different by very, very little, right? Because log n, as I say, it's like smaller than any n to the power of any constant, positive constant, right? I told you earlier. So this and this they are very, very close.